Now that we know how to write the expression of Kc, we will look into how we can actually solve and quantify a value of Kc. There can be a couple different type of questions you can get in to calculate Kc. So we know that Kc is, the expression is concentration of products divided by the concentration of reactants. What is important to remember here is that these concentrations of product and reactants are basically the concentration at equilibrium once the reaction has reached equilibrium. Okay, so these concentrations need to be determined at equilibrium. So if the question gives you the concentration of the product and reactant at equilibrium, you simply take those values, plug them into the formula, into the expression, and get your answer. But however, if the question does not give you the concentrations at equilibrium, we will have to use something which is called as a reaction table, or it's also called as an ICE table. Here I basically stands for the initial concentration of the reactant and product, C stands for any change that occurred, and E stands for the equilibrium concentration. So these equilibrium concentrations are the ones that go into Kc. We'll look into how to actually solve. Okay, so let's look at a couple questions. In a study of the concentration of methane to other fuels, a chemical engineer mixes gaseous methane and water in a 0.32 liter flask at 1200 Kelvin. At equilibrium, the flask contains 0.26 moles of carbon monoxide, this many moles of hydrogen, these many moles of methane, these many moles of water at equilibrium. Calculate Kc for this process at 1200 Kelvin. So the question is basically telling us you have at equilibrium, the important word here is that at equilibrium, this is the equation, this is the reaction that is occurring. At equilibrium, the flask consists of 0.26 moles of CO, 0.091 moles of hydrogen, 0.041 moles of methane, and 0.17 mole of water. So this is what we have. And other information it tells us is that the temperature is 1200 Kelvin and the volume of the container or the flask is 0.32 liters. Now the question is asking calculate the Kc at this given temperature. So if I want to calculate Kc, first thing I need is the expression of Kc. So based on the reaction, Kc will be products. All of these are gases, so all of them will be included in the expression. This would be CO, concentration of CO multiplied by concentration of hydrogen cubed because of the coefficient here, divided by CH4 and water. So this would be my expression. What I need now are these concentrations at equilibrium. And remember, this is concentration. Concentration meaning molarity. Molarity is moles over volume in liters. So what's given to me is concentration at equilibrium in moles. I know the moles, I just have to figure out the molarity. You cannot plug in moles into this expression, you need molarity. So how can I convert this to molarity? I have moles, I have the volume given for each. So basically I take the moles divided by the volume and that would give me the molarity. So I can figure out at equilibrium what is the molarity for each of these. You take each, you divide it by the volume. And we solve for what is the final concentration. So if you plug this into your calculators, you would get this as 0.13 molar. Water will be 0.53 molar. CO is 0.81. And hydrogen gas is 0.28. So now that I have molarities for each of these, I can plug those values in here. CO 0.81 times 0.28 cubed divided by 0.13 times 0.53. Plug this into your calculator and solve for your value of Kc. If plugged in, it gives me 0.26. So that would be my value for Kc. So as long as the concentrations at equilibrium are given, you just can plug those values directly in. Somehow figure out what is the concentration at equilibrium. Okay. Let's look at another question. In order to study hydrogen halide decomposition, a researcher fills an evacuated 2-liter flask with 0.200 moles of HI. So we have a 2-liter flask which is filled with 0.200 moles of HI. 2.00 liter is the volume of my flask, and allows the reaction to proceed at 453 degrees Celsius. So this is the amount that the researchers started with. This is the initial amount of HI before the reaction began. At equilibrium, HI is 0.078. So this is the concentration at equilibrium. Calculate Kc. First thing, when I look at the reaction, I know what is Kc. Kc is going to be concentration of iodine to the power of 1. Concentration of hydrogen to the power of 1 divided by HI concentration squared. But again, I need all these values at equilibrium. Only value that is given to me at equilibrium is HI, which is this, which means I need to find what are these concentrations. If you have a question where the equilibrium concentration of any component that you need for your Kc expression is not given to you, that means there's no other way. You would have to use an ice table. Okay. Most of the questions would require you to make an ice table. So your answer essentially lies in making an ice table. Okay. So first thing, how would we make an ice table? I'll just rewrite the equation. 2HI gives hydrogen and I2 gas. Now initially the question tells me that I have 0.20 moles. Remember, in these expressions I always use concentration. So my first step would be to convert these moles into concentration. So HI concentration will be 0.200 moles divided by 2.00 liters, which gives you a concentration of 0.100 molar. So I have my concentration of 0.100 HI, which was initially. So when you make an ice table, it consists of the initial concentration, the change followed by the equilibrium concentration. Okay, what are these? Initial is what you started with. So when I started my reaction, the question tells me the researcher has 0.100 molar HI. Again, this is an ice table where we only use concentrations. You cannot use moles here. So I started with this. Do I have any hydrogen in the beginning? 0 and 0. Because I started with only reactant in the beginning, before the reaction started, I should not have any product. So that is why I put zeros here. Change is basically how much reaction occurred and what would be the change. So change is based on stoichiometry. Okay, so based on this reaction, you can say that for every 2 moles of HI that would have reacted or that would have decomposed, we would have gotten 1 mole of hydrogen and 1 mole of iodine. How do I know this? We know this from the stoichiometric coefficient. So for every 2 moles of HI, if nothing is written, that is 1 mole of hydrogen would have been released and 1 mole of iodine would have been released. So we will use the same stoichiometry ratio, but now in terms of molarity. So this is the info that is given to me. So what would be the change? So every single time, if I'm making 1 mole of this, I have to use 2 moles of HI. So I will assume that the amount of HI that I used is 2x. And this would be a negative change. Why? Because this is a reactant. Reactants are being used up. So the change will always be negative, meaning its concentration is going down as the reaction is progressing. So that is why I put a 2 minus 2x here. If 2x of HI is used, how much of hydrogen will be produced? X. And how much of iodine will be produced? Also X. Again, for every 2 moles of this, 1 mole of hydrogen and 1 mole of iodine is produced. Only difference here is we are not working with moles, we are working with molarity. So whatever your coefficients are, just make sure you carry those coefficients in your change. Reactants are always going to be negative and products are always going to be positive change, because the concentration of product goes up, concentration of reactant goes down. So at equilibrium, we will have how much? The concentration at equilibrium is always going to be your initial plus the change that happened. Okay, so in your ICE table, equilibrium values are going to be equal to your initial plus change. So in this case, my initial is 0.100 plus the negative 2x, which would give me minus 2x. I'm adding these up. It's just that this value is negative to begin with. This would be 0 plus x, which would be x. Iodine will be 0 plus x, which would also be x. Now, what does the question tell me? Once you have your ICE table, figure out your equilibrium concentrations and then see what is the information that question is giving you. Is there any information that you haven't used, and is there any information that you can use to solve for this x? Our aim now is going to be solving for x. What is my HI? HI at equilibrium question says is 0.078, which means this is my concentration at equilibrium that I just figured out. I can simply say that at equilibrium, HI is 0.078 molar, and based on my ICE table, this number is 0.100 minus 2x, which is equal to 0.078. Now I'm simply solving for x. If you solve for x, if I'm solving for x, which means I need to get rid of all the other numbers next to it. So if I subtract 0.100 from here and I subtract 0.100 from here, I'll be left with negative 2x. Okay, so I'm just solving for x now. So negative 2x is going to be 0.078 minus 0.100. Which gives me negative 2x is negative 0.022. Now both sides are negative, so I multiply by negative 1. That would give me 2x is 0.022, which would give me x is 0.011. I divide both the sides by 2 to get rid of this 2, and I get my value of x. So now you have x figured out. The question wants me to solve for Kc. Kc means what is the concentration of iodine? The concentration of iodine, as I can see from my table, is x. Concentration of hydrogen is also x, and I know what are the values of x. And concentration of HI is this, which I already know is equal to this value given to me. So now you only have to plug all these values into Kc expression. So now if I plug these values here, Kc is going to be x, which is 0.011, multiply by hydrogen, which is also x, 0.011, divided by HI, which was 0.078 squared. So again, where am I getting these values from? My iodine at equilibrium, you can see here from my ICE table, tells me it's x. Hydrogen is also x. So my expression for Kc, if I want to write in terms of x, is going to be Kc will be x multiplied by x divided by HI squared. HI is already given to me, so that's why I'm not plugging this in. But if you plug this in and solve for x, that basically is the same thing. It would give you the same number. So now I can solve for Kc. If you do that, the value that your calculator will give you is this, and that would be your final answer. So the question, how to solve for Kc, depends on what is given to you in the question. Kc expression, you guys know how to figure it out. Now you just have to find these values at equilibrium for concentration. If they are given, plug those in. If they are not given, you will have to make an ICE table and solve for the missing information. Okay, that's another type of question. Let's move on. Another question. In a study of carbon oxidation, an evacuated vessel containing a small amount of powdered graphite is heated to 1080 Kelvin. Gaseous CO2 is added to a pressure of 0.458 atm and carbon monoxide forms. At equilibrium, the total pressure is 0.757 atm. Calculate Kp. Okay, so again, just write down the info that is given to us. It simply states gaseous CO2 is added to a pressure of 0.458 atm and carbon monoxide forms. So we started with 0.458 atm of carbon dioxide and some CO is being formed. At equilibrium, the total pressure is 0.758, meaning at equilibrium, whatever is left behind, the total pressure at equilibrium is 0.757 atm. The question is find Kp. Again, given the equation, first thing you should always do is write your expression of what is needed. Kp is going to be pressure of carbon monoxide squared divided by pressure of CO2. Oops, come on. Kids. Pressure of CO2 to the power of 1. So now what I need are these pressure values. Again, because this is equilibrium, I need these values at equilibrium. What's given to me is CO2 initially. So this is my initial, which means if I'm missing any of the information, I have to make a nice table. So initial, change, and equilibrium. So what is my initial here? We will only include the components that are in this expression. So why did I not include this carbon? Because it's in the form of graphite, meaning it's a solid. So we don't need that in the expression. So now going to this initial, I have CO2. Initially, your products are 0 unless the question says you also had product to begin with. So in this case, it doesn't say anything about product being there from the beginning, which means it is 0. This would be minus x change. Why? Because the coefficient. Whatever your coefficient is, that's what goes in front of x as well. This would be 2x, but this would be positive because it's a product. Reactants are negative, products are positive. Which means at equilibrium, I have 0.458 minus x, and this would be 2x. So what would be my Kp now? My Kp is going to be 2x squared divided by 0.58 minus, okay, which means I just need to solve for these 2x and this, and if I have those, I can plug those in here. So first thing I'll have to do is solve for x. What is the information that is given to us that I haven't used yet? Total pressure at equilibrium is this. What is the total pressure based on your equilibrium chart? Based on my ice table, I have CO left and I have CO2 left. So total pressure is going to be sum of all these pressures. So if I take the pressure coming from CO2 and pressure coming from carbon monoxide, that should be equal to 0.757 atm as the question tells me. So let's solve for x using this equation. 58 minus x plus 2x is 0.757 atm, meaning x is going to be 0.757 minus 0.458 atm, which gives you your value of x as 0.299 atm. So this is my x now. Now that I know x, I can solve for what is the equilibrium for CO and what is the equilibrium for CO2. So what would be this? P for CO at equilibrium is going to be 2x, which is this x multiplied by 2, which would give you a value of 0.598 atm. Similarly, I'll solve for pressure of CO2 at equilibrium, which is going to be 0.458 minus 0.299. The value I have is, what does my calculator give me? Let me see, 0.159 atm. So now I have pressure of CO2 and CO at equilibrium. So the last step is to plug all these values into my Kp. Kp is going to be CO squared, which is 0.598 squared divided by 0.159, and finally solving this gives me a value of 2.25. So that is my final answer for Kp. Now remember, Kp and Kc are unitless terms, so that is why we are not including any units, or we are not solving for units, we are not cancelling units out here, because it's basically just a number, a unitless term. So I don't care about units here. So this is like a second type of question that you can get for equilibrium. The idea is still the same. Make an ice table if you do not have all the information given to you. Okay, it can be Kp, it can be Kc, it doesn't matter. The rules are still the same. You need the equilibrium concentration one way or the other. Okay, I'm going over one example of each type of question you can expect. So this is like another type. Let's look at another type of question like this. Okay, if 0.250 moles of carbon monoxide, 0.250 moles of water gases are placed in a 125 ml flask at 900 Kelvin, what is the composition of the equilibrium mixture? At this temperature, Kc is given. So what the question tells me is I have 0.250 moles of carbon monoxide and 0.250 moles of water in a 125 ml flask. So this is my volume at a certain temperature, and the temperature is not changing. And the question also tells me Kc is 1.56. The Kc is given to us in this case. It is asking what is the composition of equilibrium mixture, meaning what all is present and how much of each component is present at equilibrium. Okay, so again, if I need to find what is present at equilibrium, there's no other way but to make an ice table. So I will have to make initial, change, and equilibrium. So an ice table for this. All of these are gases, which means all the components will be included in my ice table. And now we just solve for each of these. How? Remember, in ice table, only number that is added is a molarity. It has to be concentration. You cannot use moles. What's given to me here is moles, which means I have to convert it into concentration. Molarity, which is moles over liter. Liters are given, ml is given. I convert that to liters. That would give me this. So whatever you solve for it, and that goes in your initial concentration. So the initial concentration that I have for CO is 2 molar. If you solve for this concentration, it gives you 2 molar. Same for this. Do I have any CO2 to begin with? No, the question doesn't tell me I have any. Hydrogen, the question doesn't tell me I have any. Now we go by the chart. The stoichiometric coefficient. Change would, in this case, would be minus x. Again, a reactant. Minus x, plus x, plus x. All the coefficients are 1, so my coefficient in front of x is also 1. What do I have at equilibrium? 2.00 minus x, 2.00 minus x, plus x, meaning 0 plus x is x, and x. This is what I have at equilibrium. Now the question is saying, solve for these values, individual values. How can I solve for it? I have to solve for x, meaning I need an equation. I need to find the information that I haven't used, which is Kc. Kc is 1.56, which means what is Kc for this? Kc for this equation will be CO2 concentration times hydrogen concentration divided by CO concentration times water concentration. This value is 1.56. Let's plug in all the numbers that we have here. CO2 is x, hydrogen is also x. So x times x x of this multiplied together gives me x squared divided by 2.00 minus x for CO and 2.00 minus x for water. Multiplied together, that basically means I have x squared divided by 2.00 minus x also squared. Now I have to use this equation to solve for x. All of this is equal to 1.56. We just have to solve for x using this equation. How can I solve for x? Everything is squared here, so if I take a square root of the whole equation, that would get rid of these squares and that would give me square root of 1.56, right? So now I can solve for x from here. X, if you solve for x here, I'm just going to solve it in the space that I have up here. X is going to be square root of 1.56 multiplied by 2.00 minus x, and if you solve for x from here, the final value of x that I have is 1.11. Okay, it is going to be, if you take square, let me do this just in case. Square root of 1.56 is going to be 1.25, and because this is here, multiply by 2.00 minus x, that if you plug this, solve this value, x is going to be 1.11 molar. Now that I know what is my x, I can find what is the component that is present. I have x of this, which means I have how much CO left. I'll just put the answers here. CO2 that I have is 1.11. Hydrogen that is left is also 1.11 x. The CO that I have left is same as water, which is 2.00 minus x. So 2.00 minus 1.11, which will give you 0.89 molar. So that is your final answer. Okay. Hope everybody knows how to solve for x using this. You will open up these parentheses, 1.25 multiplied by 2, 1.25 multiplied by x. Then move this 1.25 minus x to this side, which would make it a plus, and then solve for x. Okay. That's another type of question. So basically all the questions will be very similar. You just have to figure out a way to solve for x. Okay. This is the last type of question you can get. Phosgene decomposes by the reaction of this. This is phosgene, COCl2, gives us CO and Cl2. Kc is given to us. Calculate the concentration of CO, Cl2 and COCl2 when the following amount of phosgene decompose and reach equilibrium in a 10-liter flask. So it has two parts to it. First part is, if you have 5 moles of phosgene, how much of COCl2 and COCl2 will be left at the end of the reaction at equilibrium. Okay, so again the question is asking to solve for equilibrium concentrations, which mean I need ice table. So we'll start with the ice table here. COCl2 gives me CO and Cl2. What am I starting with? In the beginning it says you only have 5 moles of COCl2, which means my CO initially is 0, Cl2 initially is 0. How would I find the concentration? It would be 5.00 divided by 10.0 liters, which will give you 0.500 molar. So initially I have 0.500 molar of COCl2. Initial, change, and finally equilibrium. Okay, so let's solve for my change. My change here is going to be minus x plus x plus x. 0.500 minus x, x, and x. Now again, what is the information that I haven't used yet is my Kc, which means this question is telling me that Kc is this, and I know from my expression Kc will be Cl2 times CO divided by COCl2. So in this case, Kc is 8.3 times 10 raised to power minus 4 is going to be Cl2, which is x, multiply by CO, which is also x. So x squared divided by 0.500 minus x. Okay. Now, if you look at this equation, I have the equation already. I just have to solve this equation and get my value of x. Once I have x, I plug those in here and I calculate what is COCl2, what is CO, what is Cl. That's what the question is asking. But the problem is I have to solve this equation. Whenever you have these squares in the equation, if you remember, this is a quadratic equation. Okay, if you have this x, if you will solve for x, the first thing you would do is get rid of this, which means you will move this 0.5 minus x over here, multiply it with this, and eventually if you solve for it, you will get a quadratic equation. A quadratic equation is something that looks like this: x squared plus x plus a value, let's say c, gives you equal to 0. So you might have used these equations sometime in math. Ax squared plus bx plus c equals 0. These equations are a little tricky to solve. Okay, so what do? As chemists, we try and make assumptions so we don't have to do this much math. Okay, the assumption though in this case is what? If you look at your value of Kc, it is 8.3 times 10 raised to power minus 4, meaning it is 0.00083. It's a very small Kc, right? And what is Kc? Kc is product over reactants, which means because this value is so small, my products are actually really small. My reaction is staying more towards the reactant. My reaction equilibrium lies towards the reactant, towards the left side. So I am making very little product, which means I can assume that the product that I'm making is a very small value. What is my product? My product here is, if you can see from this equation, it is x. How much of product am I making? X. So I can make an assumption here that x is a really small value. If x is a small value, I can also make the assumption that 0.500 minus this very small value is almost same as 0.500. And that would help me reduce this equation and solve it very easily. Okay, so again, what is my assumption? Because my Kc is a very small value, I'm assuming that 0.55 minus x, which is a very small value, is same as 0.500. So basically I'm trying to get rid of one of these x so that my equation is no longer quadratic and it's like a normal algebra question. Okay, so if I make this assumption, what do I get? I get my equation is reduced to 8.3 times 10 raised to power minus 4 is equal to x squared divided by 0.500, because I assume that 0.500 minus x is almost same as 0.5. Now, what is your x squared? If you rearrange it, your x squared is 8.3 times 10 raised to power minus 4 multiplied by 0.500. And what is x? Square root of this whole thing. That's it. Your quadratic equation is solved. You get your value of x. If you solve for x from here, it gives you a value of, let's go here, it will give you a value of this 2 times 10 raised to power minus 2, which is basically 0.020. Again, you don't have to write it in this form, I'm just explaining it. This is my value of x, and so you can see how, based on my assumption, I said 0.5 minus 0.020 is almost 0.5. Okay, that was my assumption. But because I'm making an assumption, I have to prove that my assumption is actually correct. So whenever you make an assumption, you will have to do one extra step, which would be check that your assumption is justified. How do you check for it? So you simply take your value of x that you got and you divide it by the initial concentration of your reactant. Initial reactant concentration, always. And if it is less than 0.05, you can simply say your assumption is justified, meaning whatever answer you get here is correct. If this value is not less than and equal to 0.05, if this is not less than this value, then you will your assumption is not correct, then there is no other way, meaning you cannot make an assumption. You will have to use quadratic equation, and you will have to basically use your quadratic equation rules to solve for x. Okay, so every time you have a question where you're making an assumption, please make sure you include this step, that you are making assumption. So you will do, once you get your value of x, you are going to make sure your assumption is justified. Can you actually use that assumption or not? How would we do this? Take your value of x. For me, it is 2.0 times 10 raised to the power minus 2. Divide by initial. What was the initial concentration of CoCl2 given to me? It was 0.500. I divide it and my value comes out to be 0.04, which is less than 0.05. And that's how exactly how you will show this in your questions. If I give you a question to solve, and if you show me this on a side, just show me checking for assumption, and you show me that it is less than 0.5, show a tick mark. That means your assumption is justified and you checked for it. There will be points assigned for this. Okay, that's it. Now that means the value of x that I calculated is correct. So only thing now left to do is I have to solve for the concentration of CoCl2. What was concentration of CoCl2? 0.5 minus x. Plug it in here, get your answer. What is the value of Cl2 and Co? It was equal to x. So I just got the value here. That's it. You're done. Okay. Now let's look at a situation if your assumption is not correct. Okay. That would be part B. Okay. Part B of the question was that assume you have 0.100 moles of CoCl2. Okay. So now because I have 0.100 moles, I'll solve for the concentration. Divide by 10 liters, which will give me 0.0100 molar. Now I do the exact same thing, but my initial concentration is this. So again, I'll make an ice table. Initial is this, these two are 0, minus x plus x plus x. This is my equilibrium concentration. Initial plus the change gives me this, this, and this. I plug those into value of Kc, gives me x squared divided by this. Again, I will make the assumption here that my x is a very small value, which means my equation will become 8.3 times 10 raised to the minus 4 is equal to x squared divided by 0.0100. And now I will use this equation and solve for x. Okay, when you solve for x, your value comes out to be this. Okay, I haven't done anything, I just simply solved for the value of x. Now the next step is I have to check for assumption. How do I check for assumption? I take my value of x divided by the initial reactant concentration. Okay, my x is what? This, divided by initial is what? 0.010. So I plugged it in here and I solved for it. You don't have to multiply it by 100, that's fine. You can just simply plug this value and check if it is less than 0.05. There's no need for you to calculate the percentage. If you solve for this, it will come out to be 0.29. When you plug this in, it will give you 0.29. Now 0.29 is definitely greater than 0.05, which means my assumption is not justified. So I cannot make this assumption. So now because my assumption cannot be made, I will use the quadratic equation to solve for x. How do I solve for x? Let's look at how would you solve for the quadratic equation. This is how the quadratic equation looks like. You have to rearrange your equation to look something like this, which would be ax squared plus bx plus c equals 0, meaning you want all your values written on one side of the equal and the other side of the equal should be basically 0. That is a quadratic equation, and it would always consist of x squared plus something x plus something else without any variable, without any x, and make it equal to 0. Now how do you solve for x from here? X from this equation, when you get your equation in this format, whatever is the number next to x squared, that is your a. Positive or negative, including the sign, that is your a. Whatever is next to x is your b, including the sign. If it's positive, it's positive. If it's negative b. Whatever has no x associated with it is your c. Plug those, take those value, plug it into this expression. minus b plus minus square root of b square minus 4ac, everything divided by 2a. That would give you your value of x. Okay, for example, let's try it out. The equation that we had initially, if I remember it correctly, it was x squared divided by 0.0100 minus x, and that was equal to 8.3 times 10 raised to power minus 4, right? So if you solve this equation, you have to rearrange that equation to look something like this. Okay, let's rearrange it. That would give me x squared is 8.31403. That's it. There's no 1 4. 8.3 times 10 raised to power minus 4 multiplied by 0.0100 minus x. So x squared is, open the parentheses, that would give you 8.3 times 10 raised to the power minus 6 minus, because this is a positive, minus x. So it would be 8.3 times 10 raised to the power minus 4 times x. Now you have this equation. I want it in this format, so I have to rearrange everything so that I have 0 on one side. So what would it become? It would become x squared. I move everything on the other side, which means this is negative. So I add the same value here, which I add the same value there. 8.3 times 10 raised to the power minus 4x, negative 8.3 times 10 raised to the power minus 6, and everything is equal to 0. So now this looks exactly like this equation. So what is my a here? There's nothing written here, which means my a is 1. This right here, including the sign, which is a positive sign, is my b. This right here, including the negative sign, is my c. Now you take all these values, plug them into this equation and solve for x. And this you only apply if your assumption cannot be justified. Okay, most of the cases I will not give you a question like this in exam, but at least you should know how to do this. So if there is a question like this, you can use that expression. So please do not assume your assumption is justified. Always confirm it, because there would anyways be point assigned to it. Okay, so if you plug this in into this expression, x comes out to be two values. Because why would it give you two values? Because here you can see it's a plus or minus. What exactly does this mean? It means you have to get two values. One time you will do minus b plus b square minus 4ac over 2a, and another time you will solve writing minus b minus square root of b square minus 4ac over 2a. One of these will give you a value which is positive, one of these will give you a value which is negative. Now based on your situation, you just have to choose which one is a good value. Only one of those values will work for you. Most of the times the positive value of x is going to work for you, because a negative would not, because your product cannot be a negative. If you never started with any product, if your product initially was 0, you cannot get a negative x for it. Okay, so most of the times you would get a positive x value and a negative x from your calculator. The negative you can ignore, keep the positive. Okay, the positive x value for me was this. Oops, was this right here. So we use this value of x. Now that I have x, I plug it into the equation. CO and Cl2 is this. COCl2 is 0.101 minus that. Okay, that is the last type of question you can get for this particular ICE table. Okay, remember, only important thing here is, if you are making an assumption, you have to prove it. It's very helpful when you make the assumption, because we don't want to use that quadratic equation. So assumption is always that x is a very small value. X can be neglected. That is always your assumption. How would you confirm it? Every single time x divide by your initial a. If it is less than and equal to 0.05, assumption is correct. If it is greater, then the assumption is not correct. Okay, you don't have to do the percentage. Percentage simply is just take this, multiply by 100. You can ignore that. Just remember this 0.05. Okay. Let's try one last question. This is the equation. In one experiment, I have 1 mole of CH4, 1 mole of CS2, 2 moles of H2S, and 2 moles of hydrogen are mixed in a 250 ml vessel at 960 degrees Celsius. at this temperature Kc is given to us. The question is, in which direction will the reaction proceed to reach equilibrium? So the first thing is, which direction will the reaction go? Remember, how do we figure out the direction is by comparing Qc and Kc. So first thing I'll have to do here is I'll have to figure out what is my Kc. Kc is given to me. I'll have to figure out what is my Qc. What is the difference between Kc and Qc? Kc and Qc have the same expression. Only difference is Kc is the concentration of product and reactant at equilibrium, and Qc is concentration of product and reactant at any given time t. So for example, in this case, at a certain time t, you have 1 mole of this, 2 mole of this, 1 mole of this, and 2 mole of this. Okay, so I will plug those values into my Qc, get my value of Qc, compare it to K, and that would tell me which direction will the reaction go. Okay, important thing is these are moles. Convert these into using the volume, convert these into molarity. So let's convert them. This would give me 1.00 divide by 250. So divide everything by 0.250 in liters. That would give you your concentration. So these are my concentrations for CH4, H2S, CS2, and hydrogen. Then I plug those into my expression of QC, which is CS, because my equation, let me write it down here, was CH4 plus H2S2 gives me CS2 and 4 hydrogen. That was my equation. So my expression becomes CS2 to the power of 1, hydrogen to the power of 4, methane to the power of 1, and H2S to the power of 2. Plug all these concentration in, your QC is 64. Now you compare QC and Kc. Remember, your Kc is what the reaction always wants to do. And what is Kc? Product over reactant. What is my QC? Right now my QC is a lot greater than Kc. Kc value is given to you in question. Kc was given to me as 0.036. So my QC is definitely a lot greater than that. So that means because my QC is larger, QC is product over reactant, which means I currently have lot of product in my reaction. Okay, so in order to get to my value of Kc, I need to reduce the product and increase my reactant, meaning the reaction will go towards the reactant. Okay, so that tells me which direction will the reaction go. The next question, part B, was that if methane is 5.56, 5.56 at equilibrium, what are the equilibrium concentrations? Okay, so question wants me to calculate what are the concentration of everything at equilibrium. Again, if you need equilibrium concentration, there is no shortcut. You have to make the ice table. What is the difference in this question? For the ice table, it's the same manner: CH4, H2S, CS2, and hydrogen. Only difference, major difference here is, remember that in this case, initially I had reactant and product. So therefore, I don't have 0 written here. Okay, why? Because my question said that you have 4 moles of CS2 in the beginning. That is why these are not 0. They are whatever the numbers were. Okay, next thing you will notice here is the change is a little different. The signs are different. Why? Because we just saw which direction will the reaction go. The reaction will go from product to reactants, right? Which means the reaction is actually going in the reverse direction. So the concentration of CS2 and hydrogen will decrease. That is why you see a negative here, and concentration of reactants is going to go up. That is why you see a plus here. Okay, so this would be 4 plus x, 8 plus 2x, y2 because of this. This would be minus x, this would be minus 4x. Sum of everything gives you equilibrium. Now you plug everything into the equation of Kc and you solve for x. Okay, so plug all those values in. The question says methane at equilibrium is 5.56, which means I can simply say that 4x, 4 plus x is equal to 5.56. So this is my equation and I solve for x. X comes out to be 1.56. Once I have the x, plug those x values into all these concentration that you see at equilibrium. Methane is this, H2S is this, CS2 is this, hydrogen is this, and you solve for each of your x values. Okay, so that is basically the last kind of question that you can expect. Important thing in all of these is, remember, if the question says Kc, you use product over reactant, and these are supposed to be equilibrium. If these are given to you, great, use those. If they are not given, solve for these using ice table. Okay, and most of the times ice table you will have to use the x and solve for x using whatever information the question gives you. Okay. This is all the summary of setting up all these questions. There's no other way to solve these questions. Make sure your equation is balanced. Make sure you write the expression of your K or your Q. Make sure all the concentrations or all the units of Kc or Q are in molarity or atmosphere. So if it's Kp, then it's atm or pressure, and if it is like any concentration, it has to be molarity. You cannot use moles. Okay, make sure you convert moles to molarity. Then plug it the values into your ice table, solve for the value of x. The best way to solve for x is based on whatever question information the question gives you. Look what is the number that you haven't used and try to solve for x using that. If you make an assumption, make sure you solve for x using the assumption and then check for the assumption if it is justified or not. The best way is you take your x, divide by the initial, and it should be less than 0.05. Okay, and that's it. That is how you work with solving KC questions.